Okay, maybe we should start now.
Yeah.
So, good morning, everyone, and welcome to today's webinar, Teaching Modern Design of Experiments. So, my name is Paolo Chiappa. I am the academic program manager for JUMP, and I'm very pleased to host today my colleague Volker Kraft, who is a senior system engineer and academic ambassador. And yes, we have a good number of topics to cover today, and Volker, of course, will also run a live demonstration using JUMP. Before I pass this to you, Volker, the first thing I would like to do is to fix maybe a couple of concepts and also launch also a quick poll to all participants. Let's say that engineers and scientists are hired today to solve problems by performing experiments, analyzing data, and then developing and implementing solutions. We could say that industry asks academics today to teach modern applied analytics, and DOE is certainly an important piece of the puzzle, but this must be combined with other, I would say, mandatory core skill set like statistical thinking and the ability to solve problems with data. That's maybe also the most interesting part of our job. We actually learn every day in our work that it is the students themselves who are asking to learn these skills. Because eventually they don't just want to find a job, and of course a good job, but also they want to transform the industrial world as we know it today. And for example, to ensure that the development of new products is increasingly sustainable and eco-friendly. So today we want to inspire you on how to add modern methodology to your teaching syllabus and to provide you and your students with the tools to respond to this very specific demand from industry. And now let me just ask you a couple of questions about how you are teaching experimentation and also with challenges you are facing today in teaching. So I hope you will see the poll now. So let's wait 30 seconds so everybody can answer these simple questions, but actually very important ones. Especially the challenges one, I think, because there are many ways to learn such a methodology, but of course, there are always challenges also when resources are available and also the willingness of, using such a methodology to teach their students is also present. Let's maybe wait 8 more seconds. So we have left 1 minute to respond to these questions. Okay, let's close the poll now. Okay, so let's also share maybe the results with you. That's pretty much interesting, especially the first one. So these methodologies might not be taught yet. And of course, I think that most of you, most of schools, most of courses actually are still using classical DOE, like fractional factorial design or response surface design to teach basically this methodology. So that's an interesting one. And also because of challenges, lack of time, of course, definitely this is the most common one, I would say. Lack of software, of course, and real world examples or exercises. And we are also working on such topic. We have a lot of initiatives running in this moment. Maybe Volker will also be able to mention some of them. Okay, interesting answers, interesting questions as well. So Volker, I think it is time to leave it to you now. and we will talk again later. Okay.
Thank you, Paolo. Indeed, really interesting answers, and I hope I will try to really help you to make this invested time today really useful for you, also to save a lot of time in the future, and that you probably consider teaching DOE maybe a more useful, a more doable task and not such a challenge. Yeah. Getting software, that's an easy one. I think we can change this and help you easily here. But you also mentioned some other challenges, and let's have a look how easy it can be and how useful, also valuable for your students to teach them about this structured way to learn from data. Yeah, so what to expect today? I think that's not a surprise at all. That's basically the abstract of the seminar you just registered for and you are in now. So the other angle is, what can you not expect today? And I have to say, the webinar today is not really about statistics. So you will see some statistics and p-values here and there, but this is not what we want to ask you to do and to teach. We really want to ask you today to teach a methodology which is really relevant for your students. Yeah. And this can be a game changer. Yeah, and this webinar also will not be a lecture or a seminar about DOE concepts and introducing DOE, and also not an introduction to JUMP. For both, about DOE and also about getting started with JUMP, there are so many other webinars and resources online. So that's not the main focus. So we will put everything together today, and we are talking about teaching modern DOE. And in some minutes, you will also see what modern means. So let me just jump into an example and show you a design table. This is a JUMP data table. The data are experimental data. So this is data from a design, an experiment. And let's have a look at this data set first. So here in this data set, we have 5 factors. So pressure to time. These are our 5 factors, our settings. We are controlling and setting all together. And then for each setting, this is called a treatment. For each treatment, we are measuring the response. We are measuring the outcome, the output of our process or system we really care about. And in this example, this is yield. And guess what? We are looking for our factor settings, which give us the highest yield. So here you see that also you see this is a design. So this is a definitive screening design, even a very efficient one, and a modern way to create designs. But there's still this more intuitive approach around, and this is still taught, but it should not be everything you're showing your students. What is the difference here? So here you see the approach, and here we are looking at a two-dimensional factor space, x1 and x2. These are our 2 settings. And again, we are looking for the settings with the best outcome. So this is y in this example. And let's imagine we are looking for the highest outcome, so the highest Y in this factor space. What would you do intuitively? So, and still many researchers just fix one factor. So now I fixed x2, yeah, at -2. So this is fixed. And then I walk along this dimension x1, and then I look for the highest yield. Yeah, please imagine that we don't know about this colored surface yet. That's what we are looking for. That's what we want to understand. So typically we don't see this, yeah, before we get our experimental results. So we would not see this. Yeah, so, but here from these tests, maybe we do 5 or 6 measurements along the first dimension, and we get to this point here. Yeah, so where we see the best outcome. Yeah, so, and then we fix x1 there, and then we also walk along x2, and then we check the second dimension. Yeah, and then we may end up in this region here, and we may think this is the best solution, but it's not. Yeah, so you can easily see that the best solution, the highest point is here. Yeah, and the reason why we missed it is that we did not test over the whole factor space. Yeah, so we already missed the whole region here. And this is a missed opportunity. So we may have done, don't know, 10, 20 measurements, but we did not get to the really best solution. So what can you do? Yeah, you can run an experiment like this. And this is really better than just investigating one factor at a time. Yeah, so here, as I said, we are controlling multiple factors all together. And in reality, you have a multivariate problem. Yeah, so it's about multiple variables, and it's not really a best practice just to study one of the variables at a time. And how is this done? Maybe let me look at the graph builder, and here you can see that what we tested. So if we look at just 2 of our 5 factors, so just 2 dimensions. So now you see where we tested, and you see that we much better covered the whole range. At least we went into the corners of this factor space, and we also tested a midpoint, a center point, but we really covered the corners, the borders of this space. And that's a good practice to understand what's going on. And if you also look at other pairs of factors, so we see that for all 2-dimensional spaces, we are covering the full space and the corners. And if we also put our final factor into the picture, so now we see that we did not get all the points, all the same pattern for all combinations. So for instance, we only for the mid-time setting, 17.5, we also had overall center points. So here, all factors, so here in this case, agitation, modifier, and time were set to a mid value. Yeah, but the combination of all of these patterns really covered our factor space in the best way. And here you see we set each factor only to 3 levels. So there's a low, level and a high level for pressure and a mid level, and the same also for the other factors. So the experiment is done, so the measurements are added to our table already. So here we see the yield, and without doing any analysis or any modeling, so I can just pick the top yield values here, the highest yield values. So that's maybe the best outcomes. And we can already see some hints about our factors. For instance, what do you think about modifier? Is lower or higher modifier better if we want a high yield? You see, oh, higher seems to be better than lower. So if we look at pressure, there's not really any significant or clear hint or pattern between pressure and yield. But again, now we are looking at bivariate related relationships, one factor and one response. What I mentioned is we have a multivariate setting. And of course, all these factors go together. And there are also higher order effects going on, which are beyond just a simple exploratory analysis, but it's maybe a good start. So to get you better informed before you start any model. So this really means that you are more effective using a designed experiment. And with each design table, you get a script which gets you back into the design phase. So let me go back to the very first step. And the very first step was asking about the response. This was set as yield. And we also told JUMP, here's our goal. We want to maximize the response. And we want to see at least 75%. So that's a lower limit. And here are the 5 continuous factors in this case with their low and high settings. So this is starting the definitive screening design. We selected to use no blocks. We could also maybe skip these extra runs to get a minimum size experiment. And if we look at the design, so this will tell us that we should do 13 measurements, 13 runs. And here you see the sorted designs. You also see the midpoints for certain factors and also the overall center point. So that's the special pattern of a definitive screening design. But why is this so effective? Because you can learn a lot from this experiment. And learn a lot means you can make clear statements about which factor, which effect is causing which variation you see on the response. And this means here, so that we have no correlation, we have no smearing, or it's also called aliasing. So it's a very clear picture. So the effects are not correlated. So correlation is really minimized, and you can also control this. And this is good to know. And that's also a reason why DOE is so important and much better than just taking observational data, because correlation is really controlled and minimized so that you can make clear statements about cause and effect. And the definitive screening design is not only effective, it's also very efficient. So this really helps you to learn faster. And it's very efficient, and efficient means you can learn a lot with just 13 runs. And how can you learn? You take your experimental data into a model. And again, for that, you get an analysis script or even several options here. So I can run a script. Let's take this here, because this is the dedicated analysis method for analyzing a definitive screening design. So you can just click the play button and run this analysis. And of course, you see some numbers and p-values, but JUMP tells you right away what are the significant, the most important effects. And there's a first stage with main effects. And these are just 3 of our 5 factors. So as you see, pressure is gone. So what we saw here earlier, we were right. Pressure has no significant effect. So there are also some assumptions you can assume sometimes, and it's sometimes a best practice just to assume what's typically observed in industry and with real experiments in standard situations. One of the assumptions is heredity. Right? Heredity means that the higher order effects, like interactions or quadratic terms, so they can only be significant if the lower order components are also significant. So for higher order effects, JUMP only considers the significant main effects. And then the combinations found as significant are modifier and the modifier times temperature and interaction and the quadratic effect of time. You don't need to worry about statistics, as we mentioned earlier. So you see p-values, a colored p-value, that's a significant effect. But if students forgot about p-values, they can also hover over a number and then a tooltip will remember them. Hey, this is a p-value, and then how to interpret this output. I can take it from here and say, okay, let's build upon this analysis and take this into a multiple regression model now. So now we see that we have a limited set of effects here, and I click run to fit the model. And this is the outcome here. So that's a diagnostic plot, the actual versus predicted yield. So a lot of the variation is really explained by our model. What's good news? So we see a ranking of our effects, some other diagnostic outputs, and then we get to the profiler. That's really a highlight in JUMP, also for students to understand what's going on and to discuss the learning outcome. Because maybe as a standard result, maybe you would look at the parameter estimates. You could look at the parameter estimates. Looks not that exciting. You could also look at your model by showing the equation. And there's no magic. So we have the intercept, which goes into the equation here. So there's the coefficient for modifier, which goes in here. So there's no magic, and the equation tells you how to calculate yield based on the factor settings. So there's no black box, but the output here, the profiler, is much easier to understand and to discuss. So again, JUMP remembers what we want. So that's the goal we specified at the very beginning. We want to maximize, and we want to be above 75%. Let me remove the desirability functions. So now we just see the relationships between yield and our factor settings. So the significant settings. And what do we see here? We see that higher modifier is better. So that's one result. We also see that there's a nonlinear relationship with time. So of course we have this quadratic component for time in our model as a significant effect. Now, we can also see that there is an interaction between modifier and temperature. So for instance, if we set modifier at a high value, we get independent on time, on temperature, sorry, because this relationship, this curve is flat. And we can also ask jump for the best settings, which means the highest yield. And this is the highest yield we can expect on average. And these are the settings to be implemented. And then let's do some control runs and see if we get to the highest yield, around 80%. So that's just a first example looking at a design, which is a definitive screening design. Very briefly, just to remind you, why is it important? Why is it so relevant and helpful, not only for students, but also for industry, which employ the students later on? Why is it so important to teach DOE? So for instance, Imperial College, the chemistry department, they asked their industry partners in the UK, what skills do you need to solve your problems? What should we teach in our doctoral training? And the number one response was DOE as the most important skill with the highest demand. If you look at a curriculum in higher education, you see that statistics typically end at simple linear regression. So nothing more real, nothing more multivariate in many cases. So multivariate and big data is typically addressed by data science courses, machine learning today, more programming. What's nice if you want to build predictive models, but if you really want to understand a process or system, if you really want to learn, you should also think about small data sets and DOE. So this is, I think, a really relevant and mandatory area should be in any engineering curriculum. So there's a huge gap between industry and academia today, and we are really happy to build bridges and to help closing this gap. So let me show you some other examples teaching DOE. So it's all on one menu, DOE. So the mostly used platforms for optimal design, custom and augment design, but also many other classical and special purpose designs. Maybe you are a bit overwhelmed here, but the good news is that in a DOE course, you would probably just use some of them, and a better overview can be seen on the jump starter. So here we have the two, the custom designer and augment design. So the most flexible, easiest to use ones. They work like a wizard or assistant and walk you through the whole problem and all constraints and settings to set your design and to set your design according to your problem and not vice versa. Then definitive screening design, more efficient in many situations, not all, but many. Classical designs. So here in the DOE course, we typically also show screening designs, also full factorial designs, which quickly explodes with the number of runs or trials. Sometimes we also look into mixture designs, response surface designs for optimization, of course. Diagnostics are important, special dedicated ones for consumer studies, consumer behavior. special purpose designs like nonlinear, and measurement systems analysis design, a new one, and also sample size explorers to calculate the sample size or power. So if you are thinking about, are they really relevant, and why are these tools and the JUMP platforms so relevant, also relevant for my students? Just look at some customer stories, and if you go to jump.com and then jump in action customer stories, that's the place to go. And then you can also select our references, customer stories by application. So choose design of experiments, and then you see several customers, and you can read about their problems and how they solved their problems by using JUMP DOE components. So you can click on any name and then read more about that customer and the problem, maybe watch some videos and see how this problem was solved. So there are great names in different industries in most of the European countries. So I think this becomes really important as soon as a student applies for a job in industry. And sometimes we hear that, yeah, mentioning custom design, definitive screening design, optimal designs, if a student says, I mentioned this and this was a door opener for me, it was really a game changer during the interview. So that's a feedback what makes us really happy. So let me mention some other demos, exercises, or methods we suggest also to, maybe consider for a DOE course. So setting the stage, making the students think about experimentation. So one classical experiment is, of course, the paper helicopter. And here you see an example from NTNU. That was my last on-site workshop in January last year in Trondheim. And you see students climbing up a chair to get a better signal. And the signal here is the measured flight time. So we really ask the students, hey, think about helicopters. And they get a template online. There's also a blog post discussing this task. And then we ask them, build your helicopters, take some measurements, maybe put them on a sheet of paper, and then think about what you learned about helicopters, but maybe more important, think about what you learned about the experiment. And this is a JUMP data set. So this is, with online teaching, this is often done as a preparation exercise. And when the students come into class, we also show them how they could do this in JUMP. So here, this is just a straightforward full factorial design using all the combinations. We just have 3 two-level factors. Is there paper clip or not? And then wing length and width. So we have 2 times 2 times 2. We have 8 treatments. We are replicating, and then we get 3 times 8. So we get 24 runs, and then we have a flight time in here from a past experiment. And then we can show what we can learn from those data. Again, the diagnostic plot, and here we see what's important. Let's go straight to the profiler. And here we see that paperclip really makes a difference. And no paperclip is much better than helicopters with a paperclip. We also see that the width of the wing. That's not that straightforward, because with a no paper clip, we prefer a thin wing. With a paper clip, we would prefer a thick wing. So that's an interaction which is also visible and easily understandable just by looking at the profiler. And there's typically a great discussion. There are great questions, just making the students think about experimentation. So they think about, hey, let's replicate, and what's the reason for that? Maybe let's have some trial runs to have a better experience and more stable operator of the whole experiment. Also a nice idea. So this is really fun and gets the students very engaged with experimentation. So what we typically cover are also some basics, but here we just remind the students about basic statistics. And I will only mention these. So there's also the statistics knowledge portal on the web, which introduces the concepts very easily and nicely. But what we do to teach these concepts about Anova regression, we show them demonstrators, which can be found on the help menu in JUMP. They come with the software. And here students can explore maybe the concept of Anova. Oops, let's put some data in. I can draw a sample, and then I can look at the data. I can look at the group means. I can run an Anova analysis. We get to the Anova table, the standard table. So here we get significance. So there seems to be a difference between some of the groups. I could also look into power. Power is 100%. So we are really on the safe side with this experiment. But if our group means would be closer, so this would also change. So now we have a 30% likelihood to miss an important effect. So we just let the students play, and the same for regression. There's another demonstrator and where they can explore the concepts of least squares. And then we also do this in JUMP. We build a design. We can simulate response values, and you can just show what does a coefficient from a regression analysis really mean. So how to understand the coefficients. A coefficient of 0 or -1 or 1, what does it mean? And this is explained by these introductory demos, and also by simulating some values in a JUMP DOE. Then we also look into screening experiments, but still this is about classical designs, and just used for introducing some basics. It's not really used for in practice or exercises. So if you take one response here and maybe 5 continuous factors, so we explain that you can pick from a list. That's a catalog, and you can pick certain combinations, but not everything. You're not really flexible, but you could, for instance, pick this 8-run fractional factorial design, and then you can see this, and you can also see that this is a really small experiment, and here you have some correlation, for instance, between a main effect and an interaction. They are totally correlated or confounded. And it's really important to know this and to think about it before you run the experiment. So we look into diagnostics like these by using screening designs. So I started with definitive screening design, which is a most efficient design type in many situations. But the typical design platform used in industry and the most flexible one is the custom designer. And this is used to teach an optimal design. Yeah, and here you see the first stage result. So again, the same 5 factors and the yield measurements with just 12 runs. And these runs are for screening. So we look at the model. We only use main effects here. We look at the model. We do some screening. And that's quite easy because we can just drop the non-significant effects from our model. And now, if we keep these 3 models, we have 3 main effects, all linear, just main effects. And we know the main effects which are important. And then we don't throw it away. We build upon this data set. And this can be done by augmenting this design. And that's the important best practice of sequential experimentation. So you are learning step by step, yeah, and not just by a bigger single experiment. So augment design. Yeah, and then we add 8 more runs. So that's a second block. So the 2 experiments are also separated by a blocking factor. And now we can look into a model again. So now we build a model also including other terms. And again, I can reduce the model by removing the least significant effects. The blocking that had no significant effect, so that's good. So, but the quadratic effect for time is significant. So this is the final model after screening and also building a response surface model with the important factors. And now we have a more complex model, a more complex response surface we can use also to optimize and find the best settings. And for optimization and also robustness, there are several approaches and tools built into the prediction profiler, so you can move on here. So a question to ask is, what if you cannot really fix the factors at certain settings? So they will randomly vary around some averages following some distributions, and then you can specify these distributions. And now we have some jitter, some random variation on our factors. You can also add some random variation on the response measurement. And clicking simulate creates 5,000 response values, taking this random variation into account. So we are not just expecting a fixed yield at a certain average or at a certain value, 75%. No, we are expecting to see some spread on the yield distribution. And this is the histogram showing this. So let me also remove the desirability functions to make this a bit simpler. And what we see here is that we have a defect rate, and that means out of spec, lower than 75%, around 50%. So that's a Monte Carlo simulation. It changes slightly with each new 5,000 data points. But we did not optimize yet. So we can also ask JUMP to find the best settings and best still means highest yield. And the highest yield we can expect here is 82%. Now let me simulate again. So the average yield, that's the dashed line here, the average yield increased. So that's 82%. So that's much better now. We still have the lower limit, the red dashed line here. And we still have a tail of our distribution, which is below the lower spec limit. Out of spec, a defect. And after optimizing for yield, we still have a defect rate of 5%, almost 5%. And you can even take this further into a robust optimization. So what if we are not looking for the really highest yield, if we are looking for the best defect rate for all of our settings? So this is maybe if you think about yield, so there's a highest yield here, but there's also another. So where do you want to be? Do you want to be on the highest point, which is more a peak or a spike, or do you want to be on the second highest point, but there you are sitting on a plateau and then changing the factors. So in the neighborhood of that best point, you are not falling down so rapidly, and you are not getting so many defects in your neighborhood, because it's a plateau. And this can be done by running a simulation experiment, and that's all built into the profiler. So this is called a simulation experiment. You run this, then JUMP does simulate 5,000 data points, but 128 times all over the vector space. So this is a space filling design. You get an analysis tool again, you run the analysis, and on that analysis, it's a model again, but now we are looking at the defect rate, a log version of our defect rate. And if I just link the profilers, okay, that's done. So now I can optimize for defect rate, and that means find the settings with the lowest defect rate for 5,000 simulated values. And this setting is here, so the profilers are linked. So if we simulate again and again and again, so we see that now we are below 5%. So from 50% to 5% to below 1%. So these are the stages of simulation you could also teach in your course, and this really closes or finishes the journey of the whole project, finding the best settings. Some more advanced techniques, that's of course still the tip of the iceberg of what you can do in JUMP. So what if the response is not just a number, but a curve? So here we have responses, and each curve you see here for each batch is a function, and what you see down here, the target, this is our golden curve. This is where we want to be with our settings. So the question is now how to change these factors here to get as close to that golden curve as possible. And this uses another platform called Functional Data Explorer. And I don't go into the details here. I just show you the final step again. No surprise, we see a profiler, and we just maximize the desirability again. But this gives you the settings, which gets you this curve on the output. And this is really close to our golden curve, so you can see the differences and integrated error and so on, and this is minimized according to that. So this gets us closest to what we want to see as a function, output function, as possible. So this also uses functional data analysis. Another example, mixtures. So here we have a problem where we want to maximize reflectivity. This is our response. But these three factors are not independent. And this can be set on the custom designer. So here we have the milling factors, and they are mixtures. And we also have two additional categorical process variables. And look at this one here. So this gives you an idea about the flexibility you have in the custom designer, where you can set many different types of factors and mix all of these factors. And you can also say if you can set them easily or not that easy, which would give you a split plot design, and you can have constraints and many options here. But here we had to add mixtures to our problem. And then when you look at the profiler for this example, so changing one mixture component also changes the other two components, because they have to sum up to 100%. If you use more on the first stage, you have to use less on the second and third stage. So that's an example for a mixture experiment. More analytics, just mentioning, of course, also the analytics, the modeling is an interesting topic. And there are also more advanced methods than just multiple linear regression. So there's a platform called generalized regression, which also uses panelized regression, generalized linear models with non-normal distributions of your data. So we also have partial least squares, which can detect a latent structure in your factors or responses, and a very new approach. So this is called self-validating ensemble models. So here we are merging DOE best practice with machine learning. So techniques like bagging and bootstrapping, and using validation, the validation technique in JUMP, and the machine learning features. So this can really be a game changer as well. And compared to other classical DOE methods, so this SVEM method can really give you a much higher predictive accuracy of a magnitude higher than other classical methods. So this is really about small data sets, not big data, but also here machine learning can do really a great job. And if you're interested, just Google SVEM JUMP Discovery, because this was presented recently a week ago on our user conference. And it's not just about DOE, so you can also get a broader perspective and ask, what about the measurement setup? What about the systems, the operators, and so on? So the variability we see on the response, where is it coming from? So this leads you to variance components. And the variability should not come from different measurement systems, of course, or different operators using different systems. So this can be verified and checked before the experiment using the platforms in JUMP as well. Other topics are process control, control charts, capability analysis, also reliability survival. But remember that there's no border here, no limits. because JUMP can also integrate with Python and MATLAB using the JUMP scripting language. And here are 4 properties which are really unique to JUMP, where JUMP is really leading. And taking them all together really makes JUMP one of the state-of-the-art tools for DOE, and also for a most engaging tool for students you can find on the market. I would like to mention that we will send you some links to teaching resources. So here I would like to mention an online course called Statistical Thinking in Industrial Problem Solving. So this is a web page, looks like this. You can also Google this, but you will get the link later on. And here are modules which are open online courses with a certification, one about DOE, another one about problem solving and defining the problem. And you can also get the material or the slides and data sets, and also integrate the content into your course, or you can use a more blended learning approach and also send the students into these online courses to combine them with your class. So you will receive a link about that. And if you want to teach PhD students, master students, we also have a special offer for you, and this is called JUMP Academic Suite for Doctoral Training. And we will also send you this link. And this includes a 2 days JUMP course we developed together with Imperial College. And you can also watch a webinar we did with Imperial College about this course and this initiative. But we will also do a handover. We will do a train the trainer. So we would also like to allow you to teach the course or use components and content from that course in your class. And all of that is for free. And it's called JUMP for Doctoral Training. And there's also this shortcut URL here. And then finally, it's all about relevant skills. It's about what's needed in industry, what's needed for as practitioners solving real-world problems. And DOE is really at the heart of this. And the skills gap is one of the major problems and barriers here. So if you want to connect, if you are at a university, if you want to connect with industry partners, we are happy to build bridges in both ways, from industry to academia and vice versa, to help you to collaborate and to get students and new hires which are better skilled for industry in the future. And there are many ways to do this and to work together, and just a few of them mentioned here. And last 10 seconds, what are your takeaways from the webinar today? First, of course, forget about one factor at a time. So teach changing multiple factors all together, a structured approach, best practices called design of experiments. And modern DOE means teach it in a way which is relevant for students, relevant in industry, relevant in practice. It's not a green field. So if you are thinking about teaching this, we have a lot of resources, also other resources I could not mention today. Please get in touch, and we are happy to set up an online meeting and also guide you to other resources, slide decks, course material, one-page guides, case studies we developed with industry, which come with real data sets you could use, please get in touch and we help you to get started. A good starting point is also the online course, our MOOC on statistical thinking. You can use it in blended learning. You can also get the material. I really recommend to check this out. And don't forget, with any other question or if you're stuck or unsure where to start, please get in touch. And we are really happy to provide some further guidance and help. So that's it for today. I see we are already out of time. Just checking with Paolo. Paolo, hey, do we have any question?
Yes, we have a question, but maybe, I don't know, since we already are running a bit late, I think we should maybe complete the webinar now. Maybe we can respond offline to this person. And what I wanted also to run here is a final survey, final poll. This is not about DOE anymore. This is more about stay connected with us and being able to receive also emails and information about upcoming events. So let me maybe run this very quickly. So if you would like to receive occasional email notifications, again, about upcoming events and news, like the Discovery Summit conference mentioned by Volker a few moments ago, also to be informed about new initiatives that are related to the JUMP Academic Industry Program. So we kindly ask you to click yes, of course. And as Volker mentioned, we are going to send you, I don't know if today or tomorrow, an email anyway with the links Volker showed you, and also some more information about how to start. If you want maybe to spend some time also looking at the resources Volker showed you today, mentioned, and what Volker is also showing is the page where you can download for free a 30 days trial license of JUMP. That you can use right away. You can also use it in combination with the resources on the website, jump.com. And you can also run I think there are maybe 500 sample data sets embedded with the software, also with the trial license. You can use just to understand more or less a bit better, let's say, what we showed you today. Okay, so let's end this as well. Just a reminder, so these are our email addresses. Again, if you want to ask some more questions, if you maybe want to dig deeper into what you learned today, we will be available, of course, to arrange maybe another call or even a workshop. In this case, it will be, of course, a remote workshop in this moment. So thank you, Volker. Thank you to all participants for attending today. And yeah, stay tuned for new events for the JUMP Academic team. Thank you.
Thanks a lot. Bye-bye, everybody.
Bye-bye.